Hello students, welcome to the third and final lecture for week 1 of Chem 151. This is going to be about stoichiometry and limiting reactants, particularly about solution stoichiometry, which will be really important to us for our labs and calculations this semester. And we'll review a couple of the types of the reactions that you will encounter. Okay, so for stoichiometric calculations, these rely on the balanced coefficients in the balanced chemical equation. I won't go too much into balancing chemical equations. I'll kind of guide you through it a little bit, but if you need more help, let me know. So remember that these coefficients represent the relative number of reactant and product particles that must react in a reaction. So stoichiometry is based around these. They also represent not only individual particles, but you could scale them up to how many moles of each that you would need. Whoops. And since we know that we can relate the number of moles of something to the mass, how many grams, using the molar mass, we do that is definitely often a part of our stoichiometric calculations to go from mass to moles. I used to work with an older professor. He'd always tell his students, go for the mole. And so you'll want to go for the mole a lot of the times because that's how you'll relate how much of one reactant or product reacts with, to make another or reacts with another. And so the mole ratio from the balanced equation will be used as a conversion factor. Just to give you an example here, so this is an example reaction where we have one propane molecule here reacting with 5 molecules of oxygen, and then they ultimately make 3 molecules of CO2 and 4 molecules of water. And this reaction is balanced because there are this one molecule of propane has 3 carbon atoms. These 3 molecules of carbon dioxide each have 1 carbon atom, so 3 times 1, that's 3 carbon atoms on each side. Hydrogen atoms, this one propane molecule has 8 hydrogen atoms. These 4 water molecules each have 2 hydrogen atoms here, so that's a total of 8. And finally, we have 10 oxygen atoms here, and we have 3 times 2, 6 oxygen atoms in the carbon dioxide, and 4 times 1 oxygen atom in each water, so that's 10. 10 on this side altogether, and oxygen atoms on this side. This equation is balanced. So in terms of, we can write this, as I said, I just stated it in terms of molecules, but we can also scale this up to moles. So it's an equivalent 1 molecule or 1 mole. We just multiply everything by mole. 5 molecules or 5 moles, that works too. 3 molecules or 3 moles. 4 molecules or 4 moles. And we can relate these moles to a mass. So like we did earlier, we were able to calculate the molar mass. Of course, these masses come from the periodic table. I won't belabor this point. I think you guys have a lot of experience with that. But a mole of CH3 weighs 44.09 grams. And for O2, each oxygen atom, each oxygen molecule is 32 grams for 1 mole of those. There are 5 of them. It's 160 grams. And then here, so here this is all in terms of mass. 132.03 grams is the mass of 3 moles of CO2, and 72.06 grams is the mass of 4 moles of H2O. The point of showing this is to show that mass is conserved, right? All these atoms, they're just rearranging themselves, not being created or destroyed, so the total mass is the same from beginning to end. So in stoichiometry, usually what we're going to be doing is we're going to do 3 steps. We're going to usually be given the mass of a particular substance that we're interested in. We'll use the molar mass to convert that mass to a number of moles. Then we use the molar ratio in the balanced equation to convert the moles of substance A, one substance, to moles of another substance that's involved in the reaction. Then we'll use the molar mass for that substance to convert back to the mass of that substance. So stoichiometry always has 3 steps: mass to mole, mole of one thing to mole of another, and then mole of that thing to mass. It is also possible to do amounts of something. You can use Avogadro's number, which you guys are probably familiar with. How many is a mole? 6.02 times 10 to the 23. But this is less common. Usually these are the steps. And it's usually 3 steps. If you were given the mole at first, you wouldn't need step 1. Or if you're asked for moles at the end, you don't need step 3. But generally you use all 3 steps here. I think we'll demonstrate this with an example here. So when heated, copper 1 sulfide reacts with oxygen to make copper 1 oxide and sulfur dioxide. How many kilograms of oxygen are required to form 2.86 kilograms of copper 1 oxide? So here, first of all, you are given the equation written out in words. Very common. Oh my goodness, now I have to write the formulas. Yes, that's why we covered nomenclature first, but this gives us a good time to review here. Copper 1 sulfide. Copper 1. What does this copper mean? The copper 1 means that the charge on the copper is +1. Okay, so copper 1 means Cu plus 1. Sulfide, the ide tells you that this is a monatomic negative ion. 1 atom. And so we can go to the periodic table to figure out its charge. It's in group 6, so its charge is -2. So if we're writing the formula for copper 1 sulfide, it's going to have 2 coppers to give us 2 positive charges with 1 sulfur. That's copper 1 sulfide. Now oxygen, here's another thing. Written on your reference sheet that I gave to you guys are all the diatomic nonmetals. Generally, when someone says oxygen, they're not talking about oxygen atoms because you never see oxygen around. They're talking about oxygen gas, which is O2. That's going to be a part of the equation. And then likewise, copper 1 oxide will be Cu2O because the copper here is +1, the oxide is -2. You'll need 2 of them. And the other product is sulfur dioxide. Notice this is a covalent compound. So that's why it has a di prefix. So we have sulfur. There's no mono at the beginning, but there never is. So that just indicates 1 sulfur. And 2 oxygens, sulfur dioxide. Okay, so now we're ready to write out the formula. But before we do, let's think about what it is we're going to do. There's going to be 3 steps, as there always is, in this the stoichiometry. We're going to go from our mass of oxygen. So this is this many kilograms of oxygen that we're making. We're going to use the molar mass of oxygen to convert to moles of oxygen. Then we'll use the molar ratio from the balanced equation to convert moles of oxygen to moles of the copper 1 oxide, which we were asked about. Then we'll use the molar mass of copper 1 oxide to convert the moles of copper 1 oxide to the mass of copper 1 oxide. 3 steps. Mole to mass to mole, grams to moles, moles of one thing to moles of another, then moles back to grams. Okay. So our equation was copper 1 sulfide, which we figured out was Cu2S, plus oxygen, O2, gas, makes copper 1 oxide, which we figured out was Cu2O, and sulfur dioxide. But this equation isn't balanced yet, so we'll need to balance it, or at least check that it's balanced. We've got here 2 coppers, 1 times 2, and 2 coppers, 1 times 2. We got 1 sulfur here and 1 sulfur. What's not balanced is the oxygen, because we've got 2 oxygens here, 1 times 2, 1 times 2. But we only got 1 over here. And so this is going to start to kind of like a cascading effect in changing all of these numbers here. But let's try to balance, well, if we try to balance the oxygen here, if we put a 2, we'll have 4. Okay. We have what's known as the even-odd problem here. No matter what number we put in front of this oxygen, it will always be an even number of oxygens on this side. However, if this coefficient here is odd, we will have an odd number of oxygens. What I'm going to do is I'm going to start by putting a 2 in front of this one here, which will give me a even number of oxygens on the right side. The problem is that gives me now 2 times 2, 4 coppers. So I'm going to have to balance that one over here. So now I have 4 coppers. But now I have 2 times 1, 2 sulfurs. So I'm going to need a 2 here. That will give me 2 times 1, 2 sulfurs. Finally, I should count up the oxygens that I have. So I have 2 times 1. I have 2 times 1. That gives me 2 oxygens here. Plus 2 times 2, that's 4 more, for a total of 6. So if I want 6 oxygens on the left side, I'll have to put a 3. And so now let's double check my counts. I have 2 coppers times 2, that's 4. Here I have 2 times 2, that's 4. For sulfur, I have 2 times 1, that's 2. 2, 1, that's 2. For oxygen, I have 3 times 2, that's 6. Here I have 2 times 1, that's 2. Plus 2 times 2, that's 4 more. So a total of 6. We've got 6 oxygens on both sides. So we are now balanced. So there's the balanced equation. Okay. Now we're also going to need, we're interested in oxygen and copper 2 sulfide. We're going to need, or sorry, copper 2 oxide we're asked about. So we're going to need the molar mass of copper 2 oxide. It's going to be 2 times the molar mass of copper. If you look it up on your periodic table, you'll see it's 63.55. Plus 1 times the molar mass of oxygen, which is 16. And we can just verify that. So let's check for copper. 63.55. Let's look. Okay, whoops. Here we go. So we can see here copper is right here, and it's about 63.55. And oxygen right here, about 16. Okay, we seem to be good there. All right. Okay, and the molar mass for oxygen, O2, will be 2 times 16. So now we're ready to go. We're going to start with the data we were given. 2.86 kilograms of copper 2 oxide. The issue is that this is not in grams right now, it's in kilograms. We're going to want to convert kilograms to grams. So we make sure that we have kilogram here on the bottom so that kilograms will cancel. And then we want to put something equal to kilogram on the top. That is 10 to the 3 or 1,000 grams of copper 2 oxide. Okay, so now we have grams. So now we can use the molar mass. This many grams is 1 mole of copper 2 oxide. So we make sure that whatever unit is here, it's also down here because they have to cancel. And the number that goes with the grams of the copper 2 oxide is 143.10. That's going to go right there. Cancels, and we put the 143.1. And that is equal to 1 mole of copper 2 oxide. So that will go up here. And so that gives us the moles of copper 2 oxide, about 20. We can check with our calculator here. Whoops. get my calculator out. Okay, so it is 2.86 times 1,000. 1,000 is on the top here, and divide by 143.1. That equals 19.98. We round to 3 sig figs. We round the 9 up here to 20.0. Okay, so now we have the moles of Cu2O. So that was the first step. We had a little extra step here because we had to turn the kilograms to grams. So now we're going to take the 20 moles. Now we're going to use the molar ratio. We see that 2 moles of Cu2O are 2 moles of Cu2O are going to be produced from 3 moles of O2. So we have 2 moles of Cu2O. The 2 comes from right here. The moles of the copper 1 oxide will cancel, and we will get now moles of O2. And now we can move on to the next step. We want to convert moles of O2 back to grams. We put moles of O2 here, and we're going to get the molar mass to convert to grams. 1 mole of O2 is 32 grams of O2. The moles of O2 cancel. We have 32, and we have now the grams of O2. Lastly, we were asked how many kilograms. We're going to want to convert grams of O2 to kilograms. So again, always whatever units here, make sure it ends up down here. Grams of O2, and it is 1,000 grams of O2 is equal to 1 kilogram. Our grams of O2 cancel, and now we can break out our calculator again and finish this off. So we're going to have 20 times 3 divide by 2, then times 32 since it's on the top, and divide by 1,000 since it's on the bottom. We get 0.96 kilograms. Or 0.959, close enough. A little bit of a rounding error there, but it's basically the same thing. Okay. And so that was a review of a stoichiometry problem there and balancing equations. What we want to apply this to is solution stoichiometry. So you're going to be working a lot with solutions in this class. And so here I'm showing an example of a precipitation reaction. So we have silver nitrate solution being combined with sodium chromate. And when we have a precipitation reaction like this, it's a kind of double replacement reaction. The positive ion with the first compound goes with the negative ion of the second. And so we get silver being +1, chromate being -2. We need 2 silvers. We get silver chromate. And this is a solid. And so I'm going to remind you how you could figure that out. You need to keep in mind your solubility rules. I'll have a slide in the next slide. You can print that out, or you can always Google solubility rules, and you'll get the solubility rules, or you can find it in your textbook in the index. These are important. You need to remember these from Chem 150. And the other product here is from sodium and from nitrate. It's sodium nitrate. Also written here is the total ionic equation. Remember that when substances are aqueous, they completely separate into their ions. So we end up with 2 separate silver ions here and 2 separate nitrate ions here, since there were 2 silver nitrates. Here we get 2 separate sodium ions. They're not together anymore because they've completely separated when they dissolved, and 1 chromate ion. The chromate ion is and the silver ion are highlighted red here because they are the ones that make the solid. notice that in the end, the sodium and the sodium nitrate is still aqueous, meaning the sodium ions and the nitrate ions are still separate. These are called spectator ions, and they were not involved in the reaction. And so we can write a net ionic equation in which those spectator ions aren't there. We get rid of them. All that's left is the 2 silver ions, the chromate ion. They combine to make the solid silver chromate. And notice the spectator ions, the sodium was there before, it's there after. Nitrate was there before, it's there after. The big difference is that the silver ions are now stuck to the chromate ions in a solid. Okay. So how did we know that silver chromate is not soluble? Well, for silver chromate, it's not a part of these solubility rules, but we have a series of solubility rules here. Now, I'm just kind of stating these because you've learned these in the past in Chem 150 and Chem 101 for your previous chemistry classes. I'll just briefly go over them, but you should have these for reference if you don't know them already, and you definitely need to keep these in mind because you'll need to be able to predict what will precipitate and what will not when we're doing reactions later. So any ionic compound that has a positive 1 ion, a group 1 positive 1 ion rather, or an ammonium ion will be soluble. Any ionic compound with a nitrate, an acetate, or a perchlorate as a negative ion, always soluble. Chlorides, bromides, and iodides, generally soluble if they're in there, unless the positive ion they're with is silver, lead 2, or copper 1, mercury 1. Fluorides are generally soluble as well, except for lead fluoride and group 2, so calcium, strontium, barium, magnesium, so forth. Sulfates are generally soluble except some of the group 2s, calcium, strontium, barium sulfate, and silver and lead 2. So hydroxides, generally not soluble unless they're with the group 1 or with calcium, strontium, or barium. Carbonates and phosphates are generally insoluble unless they're with the always soluble ones. And sulfides are generally insoluble unless they're with the always soluble ones or group 2. So let's do an example that will use this idea. Oh yeah, I've got one more type of reaction to talk about before I do it. These are neutralizations. So these are also a double replacement reaction where the positive ion of one compound goes with the negative ion on the other. So here the positive ion is H+, the negative ion is OH-. In a neutralization, they make water. Whoops. And the positive ion on this compound, the base here is sodium. The negative ion is chloride, so they make this salt, sodium chloride. Again, you can recognize an acid because it has an H in front. You can recognize the base because they'll generally have hydroxide. So that's how you'll recognize you have a neutralization reaction. So we have a similar situation to the precipitation reaction here where we do a double replacement. We switch the ions. So the question here is, if potassium hydroxide reacts with sulfuric acid, what will be produced? Well, we should figure out what the ions are first. And so the ion here for this base is K+. That's the positive ion. And the negative ion here is hydroxide. And then the positive ion for the sulfuric acid is the H+ ion, and the negative ion is the sulfate. Oops, didn't change color for me. Sulfate. SO4 2-. Okay. So this ion will go together with this one, and the H plus will go together with the OH minus. So notice that the K is positive 1, the SO4 2 minus is negative 2, so you'll need 2 potassiums. So the result here will be that you're going to get potassium sulfate, K2SO4, because potassium is positive 1 and the sulfate is negative 2. And then what else is made is water from the H plus and the OH minus. I kind of covered it up here with the writing by accident, and so yeah. And notice here when we balance, we've got 2 potassiums here, so we needed a 2 here. And we have 4 hydrogens here, 2 times 1 plus 1 times 2, 4 hydrogens, so we need a 2 here to have 4 hydrogens. And we've got 4 oxygens here plus 2 more, that's 6. 4 oxygens here plus 2 times 1. We're balanced. Remember that we have 2 potassiums here because the sum of the charges, positive and negative, must equal 0. So we're going to do one more stoichiometry problem, which will cover 2 ideas. One is solution stoichiometry. So for solution chemistry, you won't usually have the mass given. Instead, you'll have a volume of the solution and the molarity of that solution. You can use the molarity to convert your volume solution to a number of moles like we did earlier when we were doing the making a solution with a solid. We're also going to do a limiting reactant problem. So in limiting reactant problems, you're given amounts of 2 reactants. So you're not just assuming that there's more than enough of everything else. So you have to figure out which one is going to run out first. And so to do this, you'll perform the same stoichiometry calculation twice with both amounts of reactants, and whichever produces the least is the limiting reactant. No more product can be produced when it is used up. So let's do an example that shows solution stoichiometry and limiting reactant. So the question is, how many grams of precipitate are produced when 0.2 liters of 0.5 molar lithium carbonate are mixed with 0.35 liters of 0.4 molar calcium chloride, assuming that the reaction goes completely until one of them is gone? Well, first we have to write the reaction, so you got to remember your nomenclature, you got to remember your ion charges, and you also have to remember your solubility rules to figure out which product will be the precipitate. It wasn't told to you which the precipitate will be. So we've got lithium carbonate, which has lithium ions and carbonate ions. Okay, so that's in our reactant here, lithium ions and the carbonate ions. Then we have calcium chloride. So lithium is positive 1 from its group 1, and carbonate, you should know that in your head. There are 2 lithiums because lithium is positive 1, and so you need 2 of them. And so we can write the equation Li2CO3. And because lithium is in group 1, this is soluble. Group 1 cations are always soluble, so it's aqueous here. Then our other product here is our other reactant is calcium chloride. It has calcium ions. Calcium is group 2, so its ions are positive 2. Chloride is in group 7, so its ions are negative 1. And we'll need 2 of these so that we can have 2 negatives to go with our 2 positives. And so we'll write the formula now, CaCl2. And this is also aqueous because chlorides are generally soluble, with the exception of silver, lead, and mercury 1. Silver, lead 2, mercury 1. Okay, and now we got to write the products. Remember, this is a precipitation reaction. It's a double replacement, so the positive ion for one reactant will go with the negative ion of the other. And so we'll have lithium going with chloride here. Lithium is positive 1, chloride is negative 1. And so the product is LiCl. And this has an group 1 cation, always soluble. So this is aqueous. The other product has calcium as the positive ion, carbonate as the negative ion here. And so that's +2 for the calcium, -2 for the carbonate. So we get calcium carbonate. And this is a solid because carbonates are generally not soluble and calcium is not an exception. So it's the calcium carbonate that is our precipitate here. We've identified it. Now, only after you've written the reaction correctly can you balance it. Notice I haven't even tried balancing it. Don't try to balance it till you've written everything correctly with the correct subscripts. Then you can balance it. So looking at it here, I've got 2 lithiums, but I've only got 1 on this side. So I'll want to put a 2 right there. So I'll write in my 2. Again, I wrote everything first before I even tried to balance it. Okay, and let's check everything else now. All right, so we've got 1 carbonate. This is a little tip for you when you're balancing. You can balance polyatomic ions as a chunk if they stay the same on both sides. So carbonate, carbonate, 1 carbonate, 1 carbonate. We're good there. 1 calcium, 1 calcium, 1 calcium, 1 calcium. Okay, we're good there. 2 times 1, 2 chlorines, and 2 chlorines. So we're balanced. So we have our balanced equation now. Put a 2 right there. So now we can get to the stoichiometry. So let's do that. We've got our balanced equation. And we're going to have to do the stoichiometry twice. Once for our lithium carbonate and once for our calcium chloride. We're going to start with our volume of our lithium carbonate, 0.2 liters, and the molarity, 0.5 molars. And we're going to convert here. We'll need the molar mass of calcium carbonate to get the grams though. So I've calculated it here. 1 calcium, 40.1 grams from the periodic table. 1 carbon, 12 grams. 3 oxygen, 16 grams per mole. So we can add that up. We can do this together real quick. And I always recommend that you punch along with me. So make sure you understand 40.1 plus 12 plus 3 times 16. Get 100.1 grams per mole. Okay. So now we're ready to start. We can do the lithium carbonate solution. We're going to get the moles of lithium carbonate by using the volume and the molarity. We got 0.2 liters of the solution, and we have moles per liter here. So per liter of solution, that goes on the bottom, so liters of solution will cancel here. And it's per moles per 1 liter of solution. Liters of solution cancel, and we put 0.5 moles on the top, 0.5 moles of lithium carbonate. Okay, now we're going to do another conversion factor. We're going to go now step 2 in stoichiometry, go from moles of lithium carbonate to moles of the other substance we're interested in, which is the calcium carbonate. So again, we always know what goes down here because it's always the same as what's right here. So moles of lithium carbonate, and it's 1 mole of lithium carbonate because there's a 1 or nothing written here. It cancels. And whoops, sorry, lithium carbonate was right here. This should be Li2CO3. Let me fix that real quick. Boy, that's a mistake. Oh boy. Okay, well, mistakes happen. Well, I'm going to correct this real quick. Rather than re-record the whole thing, I'll just correct my lithium carbonates here. And this one Oh boy. Would be calcium chloride. Oh no. I should have been a little bit more careful. Sorry. Please excuse my fixing real quick so I don't have to re-record everything. There we go. That will fix it. Okay. Sorry about that. Let me go back here. Okay. All right, and so now our moles of lithium carbonate have canceled. And it's 1 mole of lithium carbonate produces 1 mole of calcium carbonate. Okay, and so that's why the 1 is here. Finally, we want to turn moles of calcium carbonate to grams. And so this is the molar mass. Again, make sure what goes on the bottom is what cancels here. Moles of calcium carbonate. That's 100.1 grams of calcium carbonate. Okay, this should say moles right here. That cancels. And let's punch it in here. 0.2 times 0.5. I think I messed up. 0.2 times, clear. 0.2 times 0.5 times 1 divided by 1, then times 100.1. We get 10.01. We should round this to 2 sig figs, so that gives us 10 grams of calcium carbonate. Okay. Now, since we have 2 amounts of reactants, so we also have the calcium chloride, we need to do the same thing for the calcium chloride. So we repeat the process, but this time for calcium chloride. So we need to determine how much calcium carbonate could be made. We have the same molar mass. We had 10 grams of calcium carbonate could be made from the lithium carbonate. So now we need to figure out how much could be made if all the calcium chloride reacted. 0.35 liters of that solution. It's per liter, it is 0.4 moles. So we put the liters on the bottom to cancel. We put the 0.4 moles of the calcium chloride on the top. Okay. And then now we've got the moles of calcium chloride. We want to figure out how many moles of calcium carbonate could be made. For that, we use the molar ratio. 1 mole of calcium chloride makes 1 mole of calcium carbonate. So we cancel our moles of calcium chloride. It's 1, cancel, and it makes 1 mole of calcium carbonate right there. Finally, we want to turn that to grams. So again, just make sure that your moles of calcium carbonate cancel. This should say moles of calcium carbonate. And that is 100.1 or 100.09 grams. And if we calculate that, let's do that real quick. Punch this along with me. 0.35 times 0.4 times 1 divided by 1 times 100.1. And we get about 14 grams. So we are not going to get 14 grams of calcium carbonate. We're actually going to get 10 grams. At that point, the lithium carbonate will be all gone. So there will be extra calcium chloride, but it cannot react. You can figure out how much calcium carbonate reacted, or how much calcium chloride reacted based on the 10 grams of calcium carbonate that were made. In your homework, I actually do have you figure that out and then figure out how much was left over as well. That's a little bit extra of a challenge for you there. So this relates to part the precipitation part of the homework, and there's also a neutralization problem. So it's in parts 2 and 3 on the homework. And that's it for this video. So on your quiz, there will be elements of all of this. I'll focus more on the nomenclature on your quiz, but I'll also have one stoichiometry problem as well. So make sure to practice your nomenclature. And if you do need more practice, I'll show you something here. I do have a place where you can practice more, and I'll also mention this in the instructions, but I have a website that I made called lemchem, lemchem.com, www.lemchem.com, lemchem, L-E-M-chem. And you can practice ionic nomenclature here, and this will spit out as many problems as you like, and you can write down the answer and then reveal a full solution and ask for a new one. So if you're really struggling with ionic nomenclature, maybe this will help. And this is based off of the exact list of polyatomic ions that I've given you. Okay, so I hope that that was a helpful review for you, and good luck on your homework, and let me know if you get stuck. And I'll see you guys at office hours, and also I'll have a video for your lab as well.